Okay, so in the previous section, we defined the derivative of the function at a point to be the limit of the difference quotient. Okay, and this is the difference quotient of x naught with respect to h, that little increment h. And so we're going to investigate the derivative as a function with variable x rather than it being a number, that number being the slope of a function at a point. So this time the derivative is going to be considered for all x in its domain, or perhaps in intervals as well. So our first vocabulary word, the derivative of a function with respect to x is the function f prime, whose value at x is written f prime of x, and you guessed it, it's going to be the limit of the difference quotient. Okay, so let's do a little bit of math here. Let z equal x plus h. So when I solve for h, push x on the other side, you get z minus x there. So the derivative can be written alternatively as the limit of another form of the difference quotient, okay, all over z minus x. Okay. So this is another slope equation as well. And that's all I got to say about that. And so another definition, if f prime exists at a particular point, we say that f is differentiable at that point. And if the derivative exists at all points in the domain of f, we call f simply differentiable. Differentiable at a point, and then differentiable in its whole domain. So our notation for the derivative, we'll write the derivative, and you operate on the function. Okay, so maybe a little quick example. The derivative of the function, function 1 by x. Okay, so let's evaluate the derivative, which is the limit of its difference quotient. And I'll let you do that on your own, and you should get negative 1 over x squared. Oh, don't start over. Stop. Okay, so our first example, let's differentiate the function x by x minus 1. Solution. Differentiate the function, and it's the limit of the difference quotient. X plus h over x plus h minus 1 minus the function itself over h. And I don't really see much to do here except, I don't know, great common denominators. Minus x times x plus h minus 1 over h times x minus 1 times x plus h minus 1. That. And let's keep going. I really don't know what the answer is yet. Maybe x squared plus xh minus x plus minus h minus x squared minus xh plus x all over h times x minus 1 times x plus h minus 1. And so things happen nicely when you do the difference quotient, because that happens. X squared minus x squared is 0. Get negative x plus x. What is their additive inverse is 2. So I get the limit as h approaches 0 of negative h over h times x minus 1, x plus h minus 1. And so the limit as h approaches 0 of negative 1 by this product. Okay. Take the limit, and so you'll get negative 1 over x minus 1 squared, so you get something like this squared plus, plus minus. It's, minus 2x plus 1. There we go. Okay, second example, find the derivative of the square root function as, or for x is positive. Oh, so, you know, you can, this is the domain of the function here. Okay, because, you know, the square root function, it's like that, you know, you can't have any negative numbers inside the square root function. So, I guess that's supposed to be a, right? It's supposed to be a in the solution. Well, let me say the derivative is the limit of the difference quotient of root x plus h minus root x all over h. So limit of h equals 0. Oh, maybe let me backtrack. So you have to multiply by the conjugate of the numerator there. In the numerator and the denominator. So let's compute this. And so you get x plus h minus x, because I'm using the difference of squares, over this product. Go, that's nice. And so you can see that x minus x is 0 and left for h in the numerator, and that'll cancel out with the h in the denominator there. So we'll get the limit as h approaches 0 of positive 1 by this. And looks like we can take a limit, since, you know, there's no contradiction, you know, division by 0 in the denominator. So take h to approach 0, and we'll get 1 over root x plus root x, which is 1 over 2 by root x. B, find the tangent line to the curve at x equals 4. So find the tangent line. So that's going to be, you know, whatever the function looks like. You know, hint, hint, it looks like this. But the tangent line at a point, say that's 4 here. And so up here will be 2. So you can see that the tangent line is going to be a linear function. Okay, it's just a straight line. Nothing to worry about. So the solution. So this f prime evaluated at 4, because the derivative is a function and the thing that lives in there is a positive number. That's it lives in its domain. Is you know, the limit of the difference quotient, which we said to be 1 over 2 times root x. Okay, which is 1 over 2 times 2, which is 1/4. So this is the slope. Slope of the function evaluated at the point x equals 4. So now our end result, you know, it's going to be y equals mx plus b. So we found that, and so maybe we'll use a point slope form of a linear equation. So it's y minus, when x is 4, y is 2, equals 1/4 x minus 4. Okay, let's push 2 on the other side so we get 1/4 x minus 1 plus 2 is 1. Okay, so that's the equation of the tangent line at x equals 4. All right, let's talk about other notation. Oh yeah, because there's a lot of different ways to write the derivative ddx of the function f prime of x. This there's dot notation. Oh, this one is important, dy dx. And you can say df dx, that's fine too. Whatever ones do I have? Oh, y prime of x, or f prime of x. There's literally a lot of different ways here. I have I have this down. Use that in calculus 3. And I believe this is Leibniz notation here. This is dot notation or Newtonian notation. I'm not sure where the prime came from. Newton. Okay, and if you want to indicate where you want to take the derivative, okay, you want to do it like so. So dy dx evaluated at x equals some number I'll call a is a way to indicate that you're evaluating the derivative at a point. Maybe I should have said that last section, but for this third example, we're told to graph the derivative of the function. This function is represented in blue, okay, where at certain points we have different slopes. Say this is -1, 0, 1, 2, and to be fair, maybe we'll make this like, I don't know, 5. And so when x is -1, we have, well, okay, I want to graph the derivative. Okay, so this is our y-axis here, and this is our x-axis here. And when x is -1, looks like the derivative is 1. So, at this endpoint here, the derivative will start at 1. And so you can see that the derivative decreases to 0 at x equals 0, so it'll hit that point there. And when x is 1, the derivative is -2, so it's going to continue to decrease. So it'll hit that point at 2. Oh, did I do that? Yes, you got it. There, 0, 1, 2. This is 5 here. That's -1. When x is 1, the derivative is -2, and when x is 2, it looks like the derivative is 0, so the derivative increases to 0, and looks like the derivative will start increasing again until it attains a maximum about here, right here at this point here. Maybe that's 3, I don't know. And then the derivative attains a maximum there, and then it starts to decrease again back to 0 at x equals 5. Okay, so the derivative will increase and obtain a maximum and dive down back to 0 at x equals 5. Okay, very good. And so let's connect these dots here. So that, and I think that's pretty close. Recall from pre-calculus that uh, the limit, what do I have here? The limit of a function as x approaches a equals a limit if and only if the limit uh, x approaches a from the right side of the function is equivalent to the limit from the left side of the function. Okay. All three of these things need to be the same number. L. Okay. So I guess the definition here, a function is what do I have here? Is differentiable on an interval. Is that right? On an open interval. If it has a derivative at each point inside the interval. And it's differentiable on a closed interval if it's differentiable on the open interval. And the derivative exists on the left hand, or the endpoints, the left endpoint and the right endpoint. And let me represent that as f of a plus h minus f of a all over h, and its limit as h approaches 0 from the left side, and the limit as h approaches 0 from the left side of b plus h minus f of b all over h. Okay. So note that a function has a derivative at a point if and only if the left-hand side and the right-hand side derivatives exist. And, oh, I guess I think I messed up there, but that means the one-sided derivatives are equal.